Welcome to this short video on the complete randomized design, a numerical example. So in this particular example, remember from our previous discussion, we emphasized that we don't use CRD in the field, in the open field where heterogeneity is high. So we basically use CRD in controlled environments, which could be in a lab or in a greenhouse or a shade net. So this particular hypothetical example, I'm referring to an experiment that was conducted to test the effect of different fertilization methods. So we have different fertilizers, F1, F2, and F3. So we want to see, this experiment was to establish how does fertilizer affect the yield of tomatoes. So the yield of tomatoes is perhaps measured in grams. So these are the tomatoes at the terminal harvest point. That is, there was harvest in different intervals. But now, at the end of that experiment, we collect tomatoes, which I want to call the terminal, where we are no longer going to collect any tomatoes after that period. So at a particular terminal point, we collected tomatoes and we measured the yield. Perhaps these are grams. The tomatoes, we weigh the tomatoes and we establish the weight in grams. Let me just indicate that these are the weight in grams. So these tomatoes are in pots in a shade net. So this refers to a single pot, 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 which was subjected to fertilizer type F1. And then 7680, these are also, another pot, single pot, single pot, single pot, single pot, which was subjected to fertilizer type 2. Another single pot, single pot, single pot, single pot, subjected to fertilizer type 3. So this is the data that we have across the different fertilizers. And I want you to take note that these are the replications. Replications, we are looking at the repetitions or the number of, the number of pots per fertilizer type. So the question here, or we are required to establish if fertilizer type produces different yield of tomatoes in terms of weight. So the question would be, do fertilizers produce different yield of tomatoes? That is the question. Do fertilizers produce different yield of tomatoes on average? So we need to test this, test at 5% significant level. Now, so this, we are going to demonstrate how to go about this particular test. So, firstly, we need to get so we do this through an analysis of variance, or Anova. We do this through an analysis of variance or simply Anova. Now, for CRD, so what we need to do is to get the totals. Now, these are the totals per fertilizer type. So basically, the yi dot that we were referring to are the totals. So we add for F1, so basically you may use your calculator. So 108 plus the 100 plus 96 plus 98 plus 100. So the total for fertilizer 1 is 502. You need to verify these figures. It's 502. Then we also get the total for the second one, which is 76 plus 80 plus 75 plus 84 plus 82, that is 397. Then the last one is 100 plus 96 plus 92 plus 96 plus 92. That is about 476. Now, after when we have obtained the totals for each fertilizer type, we need to get the grand total, which is our y dot dot. So the grand total, basically we add those totals. So we are going to have 502. Sorry, let me perhaps show my calculator here. We are going to have 502 plus 397 plus 476. That is 1375. Now, so that is our grand total, 1375. So from here, we need to get, sorry, I will have to, I think I want you to take note of the totals that we have managed to get. So what I'm going to do is to get the correction factor. So that is the first thing. We get our correction factor. And remember, the correction factor is the same as y dot dot squared over TR, where the number of treatment or the number of observations, which is equal to 1375. We square this, we divide by the number of treatment, number of fertilizers with 3, number of replications 1, 1, 2, 3, 4, 5. So this will be divided by 3 times 5, which is divided by 15. So that will give us, we square our total. So let me demonstrate this. 1375 squared divided by 15. That gives us about 1260 41.6667. You know, normally you can round off, but I'm comfortable working with that and round it. Now, once we have the correction factor, what is the next thing? We need to get SS total. SST, we said it is the same as the summation of Yij squared minus our correction factor. But take note of the summation of Yij squared. We are squaring each number. So in other words, this is the same as, for us to get that summation of Yij, we are saying 108 squared plus 100 squared plus 96 squared plus 98 squared plus 100 squared plus 76 squared plus, and so on and so on. We are adding each and every number until we add 96 squared plus 92 squared. This is quite a lot of work. So we are squaring each number. That is the summation of Yij squared. So I'm going to do the process here. Follow with me on the calculator. So that is 108 squared plus 100 squared plus 96 squared plus 98 squared plus 100 squared plus 76 squared plus 80 squared plus 75 squared plus 84 squared plus 82 squared plus 100 squared plus 96 squared plus 92 squared plus 96 squared plus 92 squared. So I'm getting 127425 as the total after squaring each number and adding, minus our correction factor, which is 1260 for 1.6667. So minus, I'm going to subtract 1260 for 1.6667. That gives me a 83.3333 as SS, that is SS total. So the next thing is to get SS fertilizer. SS fertilizer, I remember giving in general terms, that is the SS treatment. SS treatment, but in this case, SS treatment has got a name, which is fertilizer. So I don't need to write it as SS treatment because it has a specific name now. So SS treatment, in this case, is the same as SS fertilizer. The sum of squares due to fertilizer. So the sum of squares due to fertilizer, let me bring back the data. Let me bring back the data. So you would realize here that the totals are 502 for fertilizer now. 502,397,476. So it will be 502 squared plus 397 squared plus 476 squared. But after adding this, now I want you to be very careful here. We divide by the number of reps. A lot of people tend to divide by 3, the number of treatments. SS treatment, we say summation of yi dot, that is the totals, those 5, but we divide by the number of replications. In this case, we divide by 1, 2, 3, 4, 5. So we are going to divide this number by 5. Then we subtract the what? The correction factor. So when we do that, we will have 502 squared. Let me just put my calculator so that we move together. 502 squared plus 397 squared plus 476 squared, right? So that is the, I can say is equal to, you see, I can even write, which is 636189 divided by 5 minus the correction factor. Don't forget that our correction factor is 126041.6667. That is the number that we got there. So I'm going to divide this by 5 minus 126041.6667. Something is not okay here. 636189 something is fishy. 502 squared plus 97 times 397 squared plus 476 squared, which is 636189, and we divide that by 5. That is 127 minus 126041.6667. Okay, that gives us about I think that is the correct answer, 1196.133. Take note that we should never get negative sum of squares. When you see yourself getting negative sum of squares, know that you have made a mistake. It is better to start and recheck the calculations, which is exactly what I had done here. So we now have our SS treatment. Remember, we said we break down the sum of squares into unexplained variability and explained variability. So this is explained variability and this is the total. So where is the unexplained variability? So in other words, we said variability can be broken down into explained plus unexplained. That is total variability. So now our total variability, that is our SST. our SST is 3083.333 is equal to explained variability is the one that is due to treatment 1196.1333 plus the SS error, which is unexplained variability. So SS error. So to get SSE, we'll say SSE is equal to 1383.333 minus 1196.1333. Take my calculator. I have 83.333 minus 1196.1333. So I'm getting 187.1997 is my SS error. Now, with all this, I now have the sum of squares due to total. So I can come now and put our Anova table. So our Anova table is the same. Source of variation. In this case, we've got fertilizer. Some variation is due to fertilizer. We've got the error or the residual. Then we've got our total. Now, this is the table. Then what is the degrees of freedom? Degrees of freedom. Remember, we said number of treatment minus 1. How many fertilizer levels do we have? I'll come back so that you see my data. There are 3, F1, F2, F3. So F3 minus 1, that will give me 2. Now, I want you to quickly get for total. The number of observation, the total observation minus 1 gives us the degrees of freedom for total. So in this case, we have 1, 2, 3 times 1, 2, 3, 4, 5. That is 15 times 3, which is 3 times 5 is 15 minus 1. So we get 14. To get the degrees of freedom for error, you just subtract the total minus the treatment ones. So we'll have 14 minus 2. Remember, SST is equal to SS treatment plus SS error. So if we are using that, now we've got 14 is equal to 2 plus question mark, which is the degrees of freedom that we want to get. To get our question mark now becomes 14 minus 2, which is equal to 12. So we put our 12 here. Now, with that, we proceed to produce our ANOVA. So we have our sum of squares. The sum of squares is what we've calculated. For the total, we got 1383.33. I can round off to 2 decimal places. There's no problem. So for SS treatment, that is SS fertilizer, we've got 1196.13. Then for error, SS, we've got 187.1.20 when I round off to 2 decimal places. Please take note my rounding. So now, with this, we now have our MS, mean sum of squares. So to get MS fertilizer, we just divide this one divided by the degrees of freedom. So it will be 1196.13 divided by 2. So I'm getting 598.07. I've rounded also. So 187.20 divided by 12. That gives me 15.6. Remember, the purpose is to get F. So check this is a table. Let me just put the lines so that all of us will appreciate that it's a table, you see? So it ends here. This is what we call the Anova table. This is what we call the Anova table. Let me see if I can increase this. Let me see if I can bring this back so that the table the entire table. Oh, sorry, the entire table is displayed here. Okay. Yeah, so I think somehow it's showing. I think our light is too much now. Okay. So the last thing, we have source of variation, degrees of freedom, sum of squares. So we need to get our F, which is F cal. Let me just write it. For calculated, F calculated. So we divide the mean sum of squares for fertilizer by error. I'm trying to bring the table. When I try to do, okay, now, yeah, it's visible now. So what I'm going to do is to divide 598.07 divided by 15.6, right? So those are, remember the formula for F cal, check properly on your notes. So when you check properly, you would realize that it is mean square, mean sum of squares for treatment divided by mean sum of squares for error. So we will get our F cal as 38.34 when I round off. So take note of this value. This is the value that we want. When we are constructing the Anova table, our purpose is to get that value. Right. Now, but what are we doing? Remember, we want to test, to answer the question, do fertilizers produce different yields? Does the different fertilizers on average gives us different yield of tomatoes? That is our question. So this has not yet been answered, but we are almost there because we now have the analysis of variance. So with this analysis of variance table, what is the next thing? The next thing is to test the hypothesis. This is to test the hypothesis. So what is the hypothesis that we are testing? The hypothesis that we are testing is H naught. Maybe let me write this so that we are on this. Let me try to zoom out so that what I'm writing will be visible. So what is our H naught? Now, our H naught will be saying the average for fertilizer 1. Mu is average for fertilizer 1. So the average yield for fertilizer 1 is the same as the average yield for fertilizer 2, which is the same as the average yield for fertilizer 3. Mu is Greek for just average. Now, H1, we are simply saying at least one mu I is not equal to mu j for I not equal to j. In short, you can even write I have written in mathematics or using symbols, but you can simply say at least one fertilizer does not produce same yield. At least one does not give same yield as the rest of the fertilizers. At least one fertilizer does not give same yield as the rest of the fertilizers. It's still the same. So we are told that we need to test at 5%. Remember the question, we were told test at 5%. So our alpha is equal to 0.05. I want you to read what a significant level is. This is the significant level. I'm not going to discuss that in this video. So, but I want you to understand, because this alpha is given when we say test at 1%, test at 5%, test at 10%, you are given that alpha. Now, so that is the one. What is the decision rule? This is a fixed decision rule for an F test. So the decision rule, you reject H naught if F cal, the calculated from the Anova now, this is our F cal, 38.34. If F cal is greater than F critical. So where do I get F cal? This one is from the Anova. That is the purpose of the Anova. We get it from the Anova. What about this one? This one, we get it from the F tables. We get it from the F tables. So now, what are we saying? We are simply saying reject H naught. If, now I have to be specific because I now have F count. If 38.34 is greater than what? What is F crit? Now, for F tables, we need to say F alpha. You see, this is where we use our alpha. F at 0.05, numerator degrees of freedom. We get the numerator, you see, the numerator degrees of freedom are the degrees of freedom for the treatments. So 2 denominator degrees of freedom, you see we were dividing. Remember, to get 38.34, we divided this number by this one. We divided 598, so that becomes our numerator degrees of freedom 2, because it is what is being divided. And the error degrees of freedom is 12. So we say 12. Ladies and gentlemen, we need to, I don't think you will be able to see, but I want you to look for F tables. They are there on the internet. You can even search for F tables. Here I have at the back of a certain textbook, I have the F tables. Just I'll display them for the purposes of making you understand what I have here. So look, these are the tables. These are the tables. So here it's written degrees of freedom for the numerator, but it's only that they are written in small letters. So these are the degrees of freedom for the numerator. And here, this automatically, the column becomes the degrees of freedom for the denominator. It's only that you can't see because the figures are too small, but I will assist you to see. Now, if you check, it's written F at 0.05. So you need to be very careful here. It must be F at 0.05. Otherwise, these tables are separated. They are not given on one page. We have F at 0.05, we have F at 0.01, we have F at 0.1 for 10%, 0.01 for 1%, 0.05 for 5%. So here I'm testing at 5%, so I have to look at the F for 0.01. Now, what are the numerator degrees of freedom? It's 2. Denominator degrees of freedom is 12. So where the 2 meet, so I have 2 and 12. Where the 2 meet, so 2 is up, you go down. Then 12, where they meet, you read off the number. In this case, I'm getting 3.89. So this number is what? 3.89. So what does that mean, therefore? Once I have this, what is the meaning of this? The meaning of this means, what am I supposed to do? Because the rule is saying I should reject if 38 is greater. Is 38 greater than 3 points? Yes, it is. So what am I supposed to do? Therefore, this is what we are going to do. We reject H naught. But when we say we reject H naught, that is not a conclusion. We need to conclude. And then we conclude. We conclude that at least one fertilizer produces or gives different yield of tomatoes. This is our conclusion. This is our conclusion. Ladies and gentlemen, I want us to take note that when we have concluded like this, to a farmer, you can't go to a farmer and say, no, the fertilizers are different. The farmer does not want to hear that. What the farmer wants to hear is, which fertilizer should I use? So in the next video, I'm going to answer that question. Which fertilizer? Because you need to recommend the best fertilizer. So for you to recommend the best fertilizer, we need to do what we call pairwise comparison or post hoc analysis. So from an Anova table, you are just able to tell whether things are different or not. But from a pairwise comparison, you are able, therefore, to say, this is the fertilizer that I can recommend to farmers. Thank you very much, ladies and gentlemen. What we've done so far is to demonstrate how to analyze data that has been generated from a CRD by fitting in or by computing or by carrying out an F-test. So what I want you to pay attention is, are you able to produce an analysis of variance table from data that has been generated through a complete randomized design? So this is basically what we've done in this video. Thank you very much. Enjoy watching.